This is a reading of Chapter 3, Electricity and Electronics. Chapter is titled Introduction to Basic Electrical Circuit Materials. All electricity and electronics is based on the fundamental concept of moving electrons through some type of material and then applying electrons to a load. At the load, the electrical energy is transformed into another form of energy, such as heat, light, magnetism. In this chapter, we shall explore methods to control the flow of electrons using common devices and materials. In addition, we will explore the conversion of electrical energy for some uses, such as lighting. Conductors. Conductors are the pathway that allow electrons to flow through an electrical circuit. Conductors can be made of various shapes and sizes. They can be made from a number of different materials. The most common conductor you will encounter is copper wiring. Copper is an excellent conductor and can be formed into many different shapes. Copper comes in round, square, stranded, solid, flat ribbon, and bar shapes. Each shape has its own unique qualities that make it best for use in some specific
applications.
Conductors vary
depending
on the type of material they are made. Copper is an excellent conductor.
Silver is an even better conductor.
However, silver is too expensive to be used in common circuits. Many high voltage lines are made from aluminum because it is lightweight, and they have a center core made of stranded steel for added strength. Brass is used for electrical mechanical equipment, such as switch parts, because of its strength and conductive properties. The actual conduction of electricity is done by transferring electrons from one atom to the next atom in the conductor. Assume that a piece of copper wire is neutral. If an electron is forced into one end of the wire, then an electron will also be forced out of the other end. The original electron did not flow through the conductor, yet the energy was transferred by the interaction between the electrons in the conductor. The actual transfer of electrical energy occurs at an amazing speed. The speed has been accurately measured, and it approaches the speed of light, or 186 miles per second. In metric terms, it is 300,000 kilometers per second. The unit for measuring the conductance is the Siemens. This unit was named after the German inventor Ernst von Siemens, who did a great deal of work in the development of telegraphy use. The abbreviation for the Siemens is the capital S. The unit formula for computing electrical conductance is as follows. G equals 1 over R, for G is conductance in Siemens, and R is resistance in ohms. The conductance of a material is the reciprocal of the resistance of the material. Lesson in safety. Your body is a good conductor of electricity. Never touch a circuit, conductor, or component unless you're sure that it is not energized. An electric current flowing in one hand across your chest and heart and out the other hand is dangerous and can be fatal. The smart technician uses only one hand when working on high voltage circuits. The other hand is kept in a pocket. Technicians who work on high voltage lines work in insulated bucket trucks or on insulated platforms. Standing on a rubber mat while working on electrical systems is a standard safety and a wise practice. While the technician is standing on an insulated material, there is no direct path to ground in case of an accidental contact with a conductor. Conductor sizes. Conductors are sized by the cross-sectional area. The amount of cross-sectional area a conductor has determines how much current it can handle without overheating. Circular conductors are arranged according to size by the American Wire Gauge System, or AWG. The larger the gauge number, the smaller the cross-sectional area a wire will have. For example, a number 14 wire is larger than a number 20, say figure 3-2. This system of wire sizes was developed over 100 years ago. At that time, no one could foresee that the demand for electrical products would make this system obsolete. Some wire sizes are now larger than number 1 conductor. A temporary solution to this problem created the next set of larger sizes. The next 4 sizes were developed are 0, pronounced oct, double oct, triple oct, and quadruple oct, or 1 through 4 oct, or 1 oct, 2 oct, 3 oct, 4 oct, etc. When it became apparent that even larger sizes would be needed, the final solution for the sizing problem, a third set of sizes, was developed. The final system of sizing is the circular mill system. The circular mill system is based on a
diameter
of the conductor measured in mils, or 1/1000 of an inch. Typical conductors larger than 4 oct are from 250 kilo CMILs or KCMs to 2000 KCMs. KCM represents 1000 circular mils, so a 250 KCM represents 250,000 circular mils. Figure 3-3 contains all the wire sizes you would normally encounter. Circular mill area is the common way to express the cross-sectional area of a conductor. As previously noted, 1 mil is equal to 1/1000th of an inch, or 0.001 inches. The number of circular mils, or CMIL, in a conductor is equal to the diameter of a round conductor squared, or d squared, where d is in mils. Therefore, a wire with the diameter of 1 mil has an area of 1 circular mil, or 1 CMIL. A wire with a diameter of 2 mils has an area of 4 CMILs, or 2 times 2. A wire with a diameter of 15 mils gives us an area of 225 CMIL, or 15 times 15, which equals 225. See figure 3-4. The circular mil is a more convenient method of expressing the size of a conductor than pi r squared, which is used to compute the area of a circle. If we must find the area of a square or rectangular conductor, their equivalent in CMILs is not difficult to find. To find the circular mils equivalent, compute the square rectangular conductor's area in square mils and then divide that area by 0.7854. For example, if a 1 inch by 1/4 inch bar of copper is to be used as a conductor, first convert the inch measurements to mils. 1 inch equals 1000 mils and 1/4 inch equals
250
mils. Then multiply the dimensions in mils to get the
area
in square mils. 1000 times 250
equals
250,000 square mils. Finally, divide the square mil area by 0.7854, which equals 318,309. This results in the original 1 inch by 1/4 copper bar having a surface area equivalent to a round conductor of 318,309 CMILs. Wire charts commonly express the electrical values for conductors solely based on their size in CMILs. To determine the current carrying capacity or resistance value of a rectangular conductor must be converted to circular mils. Wire charts commonly express the electrical values for conductors solely based on their size in CMILs. To determine the current carrying capacity or resistance value of a rectangular conductor, the rectangular conductor must be converted to circular mils. Conductor insulation. Materials with only a few free electrons do not conduct electrons well. These materials are called insulators. To keep the electron flow contained to the conductor path and to prevent contact with other conductors and people, conductors are coated. This protective coating is called insulation. As the name implies, insulation is made of insulating materials such as rubber, plastic, and other synthetic materials. There are many types of insulation commonly known today. These materials include thermoplastic, neoprene, Teflon, nylon, and polyethylene. The type of conductor insulation is determined by the application of the electrical system. In determining insulation type, many factors must be taken into consideration. Some questions one might ask would include: will the insulation be exposed to extreme heat generated by an industrial furnace or the extreme cold of a freezer in a food processing plant? Will the insulation need to withstand exposure to acidic vapors in a chemical plant or wet acidic soil? Will the cable be exposed to oil from manufacturing equipment? Will the insulation give off toxic fumes if burnt? Will the insulation in a building affect the breathable air to its occupants? Insulation coatings. Insulations are marked with code letters indicating their approved uses. Examples of these markings are HH for high heat resistant, M for oil resistant, UF for underground installation, etc. When selecting conductor insulation, all conditions must be considered. A brief list follows: R for rubber, H for heat, HH for high heat, A for asbestos, T for thermoplastic, M for oil resistant, UF for underground feeder, and C for corrosion resistant. Conductor insulation may be color-coded throughout some other electrical applications, such as an automobile. At times, the colors represent certain voltages, polarities, or grounding conductors. The color used is governed by the building codes or manufacturing associations. Uniform standards in the color coding of insulators assist the technician in troubleshooting electrical and electronic systems. Types of conductors. Conductor wiring comes in many shapes and assemblies. See figure 3-5. The conductor can be solid or stranded. There can be one or more conductors inside one cable assembly. The insulation jacket sometimes contains a metallic sheath to provide added protection against physical damage or to prevent interference from other electrical systems. The conductor assembly can be flat to accommodate special installations, or it can be designed to be installed in electrical pipe, referred to as conduit. Conductors have many applications that require a unique design to match the type of special electronic application. Some of these applications are telephone communication cables, cable television, computer lines, high voltage transmission cable, fiber optics, motor and relay windings, and marine applications. There are hundreds of types of conductors available today. Conductor resistance. Even though conductors provide a low resistance path for electron flow, they still have some resistance. This resistance must be considered when long distances are involved. There are 4 factors directly related to the resistance of conductors. Cross-sectional area of the conductor. The larger the surface area or diameter of a conductor, the lower the resistance. The type of conductor material. Different materials have different resistance values. Length of the conductor. The longer the conductor, the greater the resistance. Temperature of material. Resistance of a material rises with rise in temperature. Cross-sectional area of a conductor. Increasing the cross-sectional area of a conductor increases the amount of current that can flow. To help visualize this, use the flow of water through a pipe as an example. Figure 3-6 A large diameter pipe can carry more gallons of water per minute than a small diameter pipe. An electric conductor operates in the same fashion. The larger diameter the conductor carries, the more electrons per minute than a small diameter conductor. Types of material. As discussed in Chapter 1, some materials are better conductors than others. The type of material affects conductance and resistance. Figure 3-7 shows one example as number 12 copper wire has 1.619 ohms resistance per 1,000 feet. An aluminum conductor of the same diameter and length offers 2.57 ohms of resistance. Length of conductor. The length of a conductor greatly affects its total resistance. If 1 foot of wire has a certain resistance, then 10 feet of the same wire will have 10 times their resistance. 50 feet of the wire will have a 50 times more resistance, and so on. As a conductor becomes longer, it creates a voltage drop in a circuit. A circuit using short lengths of wire, such as an electrical lab project using 3 to 6 inches of number 22 wire, does not create a major problem, but long runs of wiring can create electrical problems. In Figure 3-8, a 10 amp load is connected to a circuit using number 22 copper wire. The load is at a distance of 100 feet from the source. When the switch to the motor is closed to connect the motor will heat up internally because an insufficient voltage is being applied. The low voltage is a result of the voltage drop along the length of the conductor. The loss of voltage can be computed using Ohm's law. Figure 3-8. The voltage drop caused by the resistance of 200 feet of number 22 copper conductor wire connected to a 10 amp load is to 32.9 volts, or 16 volts for each 100 feet of conductor. The electrons must travel at a total distance of 200 feet to make a complete circuit. The total resistance of the wiring is equal to 3.29 ohms. The current through the load is 10 amps. By applying Ohm's law to these conditions, a voltage drop equal to 32.9 volts has been created. E equals 10 amps times 3.9 ohms. Subtracting the 32.9 volt drop from the available source voltage of 120 volts leaves only 87.1 volts for the load. This amount of voltage is undesirable and will no doubt cause equipment failure, especially for an electrical motor load such as a drill. A lesson in safety. When using non-extension cords to operate lights and tools, be sure that they have sufficient conductor size. The larger the wire size used, the smaller the voltage drop created. Small diameter extension cord conductors may heat up and burn. Motor-driven tools at the end of a long extension cord can heat up and operate inefficiently. Temperature of a material. A fourth consideration in conductivity is temperature. Most metals used in conductors such as copper and aluminum increase in resistance as the ambient temperature rises. Ambient temperature is the temperature of the material surrounding the conductor, such as air, water, or soil. In many electronic products, careful design is necessary to ensure proper ventilation and radiation of heat from the current carrying conductors. Many electrical products, such as computers, have a fan installed inside the appliance to circulate heat away from electronic components. These components can be damaged by heat easily. When many conductive materials are exposed to extremely low temperatures, their resistance value approaches zero. These materials become superconductors. Figure 3-9 is a picture of a superconducting cable. Magnets can be produced from these superconductors. Early experiments with supermagnets using superconductors produced magnetic fields so powerful that the magnetic housing was crushed by the tremendous force. Since electrical motors operate on the principles of magnetism, the more powerful the magnet, the more powerful the electric motor will be. Superconductive material is also used in some magnetic imaging medical equipment. The superconductive materials have made it possible to peer deep into the human body. Magnetism and electromagnetism will be explained in detail in Chapter 9. To make a superconductor, the temperature of the conductive material must be lowered to nearly absolute zero, negative 273 degrees Celsius or negative 460 degrees Fahrenheit. Liquid nitrogen is used to cool the conductive materials to such a low temperature. Today, some materials display superconductive properties at much higher temperatures. In 1987, a team of scientists produced a superconductor at approximately negative 270 degrees Fahrenheit. New applications for superconductors are appearing everywhere. Safety organizations and standards. There are many different organizations that work together to protect the worker and the general public from dangerous conditions and hazards, such as those caused by improper wiring. These organizations create and use safety standards, which may then be adopted by government agencies. The National Fire Protection Agency. The National Fire Protection Agency, or NFPA, is an organization dedicated to fire protection. The NFPA provides information about how fires are started and the specific fire prevention methods. NFPA provides many publications dealing with topics of how to handle volatile chemicals and flammable materials. The NFPA produces the National Electric Code, NEC, which is a special publication that relates directly to your course of study of electricity and electronics. National Electrical Code. The NEC or National Electrical Code is a set of electrical standards that should be followed to ensure the safety of people and property. The set of standards was developed by NFPA and contains over 700 pages describing how electrical equipment and systems should be installed. This is the main guide used for all electrical construction in the United States. Government agencies in city, county, state, and federal levels often adopt the code in its entirety and may rewrite some of the code to meet higher standards. The set of standards define how electrical work should be accomplished and lists the minimal specifications for materials being used. Underwriters Laboratories, Inc. Underwriters Laboratories, Inc. is an independent, non-profit organization that conducts tests for the interest of the public safety. If UL tests equipment and finds that it satisfies minimal safety standards, the equipment is awarded their seal of approval. The UL seal of approval, shown in Figure 3-10, is a recognized industry standard that proves the product has been independently tested and approved as a safe product. It also ensures the products being produced will continually meet minimal safety standards. There are over 20 billion UL seals on 19,000 different types of products. Occupational Safety and Health Administration. The Occupational Safety and Health Administration, OSHA, is part of the U.S. Department of Labor and is mainly responsible for worker safety. OSHA conducts on-safety inspections of industries that have reportedly high incidents of accidents. OSHA has the authority to inspect and fine industries that do not meet minimal safety standards. For example, OSHA can inspect a facility to ensure all workers are using UL-approved non-conductive step ladders for electrical work or ensure worker areas have proper ventilation to remove any hazardous fumes. Be aware that OSHA has adopted the NEC standards. OSHA is not limited to electrical work, but it is responsible for the safety of all industries, such as agriculture, automobile, fishing, manufacturing, and warehouse operations. Conductor voltage drop. The National Electric Code, NEC, has set maximum voltage drop standard for branch circuits. A branch circuit is the wiring from an electrical circuit panel to the last device connected to that circuit. A maximum of 3% voltage drop is permissible by NEC standards. A formula for calculating the size conductor needed to stay within the 3% limit is below. CMA equals K times I times L over VD, where CMA is the area in circular mills, K is the material constant, I is the amperage, and L is the length of wire, and VD is the voltage drop. Example. First, decide the type of material to be used in wiring the circuit, copper or aluminum. The material constant, K for copper, is 12. The material constant for aluminum is 18. This is an NEC standard based on the resistance of the material. To find the size of the copper conductor needed for a 10 amp load located 150 feet from the circuit breaker panel, we must multiply the material constant times the amperage times the length, K times I times L. Remember, the length is twice the distance from the panel. Next, divide by the permissible 3% voltage drop. The voltage in this case is 120 volts. 3% of 120 volts is 3.6 volts. Just naming the formula here. CMA equals to 12 times 10 times 300 all over 3.6, which equals CMA of 36,000 over or divided by 3.6, which equals to CMA equals to 10,000, or a number 10 copper conductor is needed. This formula is very handy when trying to determine a conductor size that will not cause significant voltage drop. Excessive voltage drops prevent electrical equipment from operating properly. Review questions for section 3.1. A half inch is equal to 500 mils. A cross-sectional area of a conductor is measured in CMILs, or circular mils. The unit of measure for conductance is the Siemens. What is the circular mil area of a number 22 copper wire? Number 22 copper wire equals to 1022 circular mils. List 4 factors that affect conductor resistance. 1. Cross-sectional area. 2. Temperature. 3. Length. And 4. Material. What is the resistance value of 500 feet of number 4 copper conductor? The formula is resistance of 0.2533 ohms divided 1 kilo feet, 1,000 feet, which equals to 0.12665 divided 0.5 thousand feet. Section 3.2, Special Conductor Pathways. There are several special conductor pathways used in electrical and electronic work. They are the breadboard, printed circuit board, and the metal chassis. These pathways serve special needs, yet their main purpose is the same as any other conductor, to provide a good conductive path for electron flow. Breadboards. A breadboard is a useful device for learning about circuits. A breadboard consists of a series of holes aligned in rows across the entire surface of an insulation material, such as plastic. Copper strips are run in parallel under the rows of holes and are used as conductor pathways. Electronic devices such as resistors and transistors are inserted into the holes. Jumper wires are then used to make additional connections between the devices. The breadboard provides an easy system for constructing circuits quickly. The boards are commonly used in experiments or to make a prototype of a circuit before the circuit is soldered or constructed in a mass assembly system. Some boards are called proto boards. See figure 3-11. Printed circuit boards. Printed circuit boards. PCBs are made from a thin layer of conductor material, usually copper foil, cut into strips and attached to an insulated board. The strips act as the circuit paths. Components are inserted through holes in the insulated board and then soldered to the conductive strips at circular spots called connection pads. The connection pads provide the extra area required for making good soldered connections. Figure 3-12 shows a typical circuit board layout. A heat sink area is a wide copper surface that is used for a common connection point for many devices, as well as to dissipate the heat generated by the electronic devices. Edge connectors provide the electrical point for attachment to other electrical equipment. The conductor paths can be less than 0.001 inch in thickness. These strips can be one side or both sides, depending on the design of the board. The currents used on most boards are very low and usually do not require heavy wiring. Construction of printed circuit boards. PCB. A printed circuit board starts out with a thin sheet of copper foil covering the entire surface of an insulating material. If the PCB is to be double-sided, both sides will be covered with a thin sheet of foil. There are a couple of common methods used to produce the circuit design on the foil. The layout of the circuit can be put on the cover using a
resistive
material. The board is then dipped into an etchant. The etchant removes all of the copper surface not protected by the
resistive
material. The board is then cleaned to remove any excess of resist or etchant. Holes are then drilled at the connection pads. Printed circuit boards can also be made using a photographic process. Light-sensitive material covers the surface of the board. A negative of the circuit board layout is placed over the board. The board is then exposed to light and developed in a manner similar to that used in photography. After developing, the unexposed areas are washed away with a solvent. The exposed area, the pattern of the circuit, remains. The board is then etched as was described in the first method. Circuit board components can be installed by hand or by automated systems. The choice is usually based on economics. If a low number of boards are to be produced, hand assembly is less costly. If thousands of boards are to be produced and assembled, automated systems are used. Chassis. In the early years of electronics, components were mounted on metallic surfaces called chassis. The chassis itself served as a part of the circuitry. The use of a chassis as a conductor is not as common today, but it is still in great use. One of the most visible uses of chassis as a conductor is the automobile. The metal frame and body parts serve as a chassis, providing a conductor path for the negative side ground of the circuit. The positive lines leave the positive battery terminal and connects to the device, such as the car's headlamps. A fuse or circuit breaker is in series with the lamps for protection. A switch is also in series for turning the lamps on and off. The return to the negative of the battery is through the frame of the car or the chassis itself. The negative conductor for the lamp simply terminates at the lamp location, connecting to the metallic shell of the car. The electrons return to the battery through the metallic frame of the car. Review questions for section 3.2. A temporary circuit is usually wired using a breadboard. The most economical way to mass produce an electronic circuit is using automated machines. The automobile is an example of a chassis wiring. Connection of devices to a PVC is usually made by edged connectors. What other type of transportation could use the frame for parts of an electrical circuit is the aircraft. 3.3. Common circuit devices. There are several common circuit devices that are present in most electrical and electronic circuits. They provide a means of controlling electron flow through the conductor paths to provide for safe operation of circuits. The three important items discussed here are switches, connectors, and circuit protection devices. Switches. Switches are installed in circuits to control the flow of electrons through the circuit. They can be categorized by their actuator and electrical switching path. The actuator is the mechanical device that causes the circuit to open and close. Various types of switches are illustrated in figure 3.14. The schematic symbol associated with each type of switch is also included. Some of the most common actuators are the slide, toggle, rotary, and push button. As you can see, the name of the switch indicates the type of actuator used to turn the switch on and off. The electrical circuit inside the switch is described in terms of poles and throws. The simplest type of switch is the single pole single throw switch, which is abbreviated as SPST. The term single pole means that the switch provides one path for the electron flow and that it can be turned off and on. The term single throw means that the switch controls only one circuit. Single pole double throw switch, SPDT, has one common connection point and can complete a circuit path to two different circuits. However, only one circuit can be completed at a time. There are many possibilities and combinations for a switch of this type. A useful application of the single pole double throw switch is its ability to control a load, such as a lamp, from two different locations.
In residential wiring systems, the single-pole double-throw switch is referred to as a three-way switch. In Figure 3-15, two single-pole double-throw switches are connected to a lamp. Either switch is capable of turning the lamp off and on. A double-pole double-throw switch has two common connection points and can provide two switch paths simultaneously. The double-pole double-throw switch is like having two single-pole single-throw switches connected in parallel. Switch ratings. Switches are rated for ampacity and voltage. The ampacity rating of a switch is an indication of how much current it can safely handle. The voltage rating is the maximum voltage for which the switch is designed. Exceeding the maximum voltage rating will cause the electrical mechanical circuitry inside the switch to fail. For example, a toggle switch is rated at 1 amp and 24 volts. A current in excess of 1 amp will burn out the switching circuitry inside of the switch. If the 24-volt switch is connected to a 240-volt circuitry, it may fail to open the circuits sufficiently to stop the flow of electrons. This action will result in a dangerous situation that can melt the switch's insulation and short-circuit the switch. Connectors. There are many types of connectors used with electrical
Conductors.
The type of connection used varies according to the type and size of the
Conductors.
the purpose served by the connection and the type of device to be connected. Figure 3-16. You will see many common types of connectors. One general classification of solderless connectors. A solderless connector does not require the use of solder to make a connection. These connectors generally require a crimping tool. The crimping tool squeezes connectors to the conductor. Figure 3-16 shows the common wire crimp on terminals and splices. Some types of connectors use screws and bolts in the form of mechanical connection to conductors. These connectors are used primarily for larger conductors. See Figure 3-17. Circuit protection devices. Common circuit protection devices are fuses and circuit breakers. Fuses, such as those shown in Figure 3-18, are constructed from small, fine wire. This wire is engineered to burn if certain amperages are exceeded. Fuses are sized by their voltage and current capacity, primarily currents. For example, a 3 amp fuse is designed to burn and open the circuit when the current exceeds 3 amps. A load that draws 3 amps or greater will generate sufficient heat in the fuse to melt the fuse link inside of the glass tube. The time required to melt the fuse link is inversely proportional to the amount of the overload. This means that the higher of the overload current, the faster the melting action occurs. When a fuse melts, it must be replaced. A circuit breaker, sometimes called a reset, is another device used to protect a circuit from overload and short circuit conditions. See Figure 3-19. The main advantage of a circuit breaker over the fuse link is that the circuit breaker need not be replaced after tripping. It can be reset by moving the handle to the off position and then returning to the on position. Some circuit breakers have an actuator similar to the push button switch. These breakers are pushed in to reset after tripping. Circuit breakers and resets require a waiting period to allow the internal trip mechanism to cool down. Most homes today use circuit breakers as a safety device to prevent overloads, and overloads could result in house fires. Circuit breakers are produced with two different tripping methods. One method uses bimetallic strips. A bimetallic strip is a metal strip made of two different types of metal. Different metals expand at different rates. Heat generated from the overload condition causes the bimetal strip to expand. The different metals expand at different rates. This causes the breaker's trip mechanism to bend and break contact. Some trip mechanisms are adjustable to allow a more precise trip
Current.
A second tripping mechanism uses magnetism to operate. The circuit current
Runs.
through a coil. As the current increases through the coil, the amount of magnetism in the coil increases. When a predetermined point is reached, the tripping mechanism operates and opens the circuit. The magnetic circuit breaker is much faster and more accurate.
Then the bimetallic circuit breaker.
The magnetic circuit breaker, however, is more expensive than the bimetallic type.
Lighting. There are many
Different methods.
in which light is produced. Light is generated when burning a variety of gases, methane, propane, liquids like gasoline, fuel, oil, and solids like wood or paper. Certain chemicals
Produce.
luminescence when mixed together. Necklaces and bracelets filled with these chemicals are often sold at nighttime celebrations. Various minerals and glow-in-the-dark toys supply light through phosphorescence. They absorb energy from sunlight through a lamp and then release this energy in the form of light when the energy source is removed. However, for most of our lighting systems, the energy source is electricity. There are two very different types of electric lighting systems. One is incandescent lamp and the other is the discharge lamp. The incandescent lamp principles. In 1879, Thomas Edison developed
The
first successful incandescent lamp. In an incandescent lamp, light and heat are created from current flowing through a filament. The first lamp was of simple construction with a
carbon filament.
inside a glass envelope to prevent the carbon from igniting. Soon afterward, the
Tungsten.
filament replaced the carbon filament.
The
tungsten,
filament proved to be a much more efficient method for producing light than carbon filament. In figure 3-20, the basic construction of the incandescent lamp is illustrated.
halogen lamp,
In a
halogen lamp,
a
tungsten,
filament is inserted through a glass tube, and the tube is filled with
halogen gas.
This type of lamp will economically produce a great deal of light. It is commonly used
In automobile headlights,
The halogen gas makes the
tungsten,
filament last longer. The
tungsten,
filament in most lamps evaporates over a long period of time due to the tremendous heat generated by
tungsten,
filament lamps. The halogen returns the boiled
tungsten,
filament particles back to the filament, thus causing the filaments to last longer. See figure 3-21.
the discharge lamp,
Operates differently from an incandescent lamp.
the discharge lamp,
Produces light by energizing a
gas such as
argon, neon, helium, or vapor of mercury or sodium. The gas or vapor is ionized by the electrical pressure and will glow, thus emitting light. A discharge lamp can easily produce 20 times more light than a
conventional,
filament bulb while using the same type and amount of electrical energy. Descriptions of several types of discharge lamps follow. The fluorescent lamp. The fluorescent lamp consists of a long glass tube coated on the inside with phosphor. See figure
3-22,
A filament or electrode is inserted at each end of the tube. The air is removed from the tube, and then it is filled
with
an inert gas and a small amount of mercury. When the tube is energized, the filaments at the end will glow. However, the filaments do not provide very much light. The filaments are used to produce heat, which vaporizes the mercury inside of the tube. Once the mercury has been vaporized, the electrons flow along the mercury vapor. Ultraviolet light is produced inside of the tube. The ultraviolet light strikes the phosphor coating and causes it to glow. This produces the familiar phosphorus light. A ballast is used to limit the current inside of the tube. The ballast consists of many turns of fine wire. The ballast is also used to produce a higher than usual voltage, which is applied to the filament in the ends of the tube. An older style fluorescent lighting used starters in their circuitry between the ballast and the lamp. The purpose of the starter was to allow the filament inside of the lamp and produce the necessary heat to vaporize the mercury. Once this was accomplished, the starter would open and cease the heating action of the filament. Newer fluorescent lamps incorporate a device in the end of the tube that replaces the need for a starter. Compact fluorescent lamp. Compact fluorescent lamps, or CFLs, are special fluorescent lamps designed to screw into a standard incandescent lamps. CFLs are much more efficient than incandescent lamps. For example, a traditional incandescent 60-watt lamp can be replaced with a 11 or 15-watt CFL and produce the same amount of light using a quarter of the electrical energy. Temperature is another way CFLs are cost effective. An incandescent lamp gives much more heat than a CFL. Replacing incandescent lamps with CFLs can reduce the cost of air conditioning. A typical spiral type CFL is shown in figure 3-23. The large base of the bulb contains the ballast that is required for fluorescent lamps. The initial cost of the CFL is higher when compared to an incandescent lamp, but the savings are realized in approximately 500 hours of use. CFLs are designed for use with both AC and DC sources. The DC type is used for recreational vehicles and portable lighting that runs on batteries. Mercury vapor lamp, shown in figure 3-24, shows the construction of a typical mercury vapor lamp. It consists of two electrodes connected at opposite ends of an arc tube. The arc tube contains a small amount of mercury and argon gas. When the lamp is energized, the starting electrode generates heat to vaporize the mercury and ionize the argon. After a considerable time, the starting electrode opens, allowing the current to flow through the arc tube. The disadvantage of this type of lamp is the long delay required when starting or when the power has been temporarily interrupted.
The neon lamp,
shown in figure 3-25, consists of two electrodes inserted in the end of a long glass tube. The tube is often heated and shaped into words or pictures for commercial applications. After being shaped to achieve the desired effect, the tube is filled with neon gas. A neon light transformer is used to produce a high voltage, 10,000 volts or more, which is needed to create a current through the neon gas. Because of the high voltage present, special high voltage insulation is used to insulate the conductors after the light is energized. The neon tube will glow. Parts of the tube may be darkened out by black paint to achieve varied designs. To create the variety of colors, other gases such as argon and helium can be used. Although these lamps are filled with gases other than neon, they're often referred to as neon lamps out of custom. Glow lamps. The glow lamp is very similar in construction to a neon lamp. It consists of two electrodes inside a short glass tube filled with neon or argon. The electrodes in a glow lamp are quite close in comparison to the neon light. Consequently, a glow lamp does not require the same high voltages required in typical neon signs. Strobe
lamps.
Strobe lamps may vary from a very short to a very long piece of glass tubing. The long strobe tubes are usually manufactured in a spiral shape, such as that shown in figure 3-26. The strobe lamp operates by discharging a high DC voltage directly through the tube. What is observed is the electrical arc flashing through the tube. Sometimes there are exciters placed along the length of the tube to help attract the electrons through the long tube. Exciters are charged lengths of wire that assist the arc along the length of the glass tube. Strobes are capable of producing flashes of such great intensity that they can be used for airfield approach systems. The flash of a strobe can generate in excess of 50,000 watts and can be observed at distances greater than 10 miles during the light of day. Lumen. Most people rate lighting brightness in wattage because they are familiar with the incandescent light. This is misleading. The amount of light produced by a lamp is rated in candelas or lumens. The candela is based upon the amount of light generated by one candle. The lumen is the term used to measure the amount of light generated by lighting systems. Look at figure 3-27 to see an illustration comparing the candela and the lumen. A candela will produce 12.57 lumens at a distance of 1 foot from its center. A 100 watt incandescent light, a typical value you will find in your home, can produce as much as 4,000 lumens of light. The chart that follows shows a comparison of light intensities. Lumens per watt, LPW, gives the amount of light produced for each watt of energy used. The higher the LPW, the more light you will receive for each watt of electricity. Edison's lamp. Edison's first lamp produced 1.4 lumens per watt. Incandescent lamps produce 10 to 40 lumens per watt. Fluorescent lamps produced from 35 to 100 lumens per watt. Halogen lamps produce 20 to 45 lumens per watt. Mercury vapor lamps produce 50 to 60 lumens per watt. Metal halide lamps produce 80 to 125 lumens per watt. And high pressure sodium lamps produce 100 and 140 lumens per watt. Resistors. One of the most common components encountered in the study of electronics is the resistor. The resistor is used to create a desirable voltage drop and limit current values in electronic circuitry. Figure 3-28 shows several molded composition fixed resistors. They are manufactured in many sizes and shapes. The schematic symbol for a fixed resistor is also shown. The chemical makeup that causes resistance is accurately controlled in the resistor manufacturing process. Resistor values can be purchased in a range of values from less than 1 ohm to over 22 mega ohm. The size and material used for resistance is rated in watts. A resistor's wattage rating refers to the resistor's ability to safely dissipate heat. Heat is generated by electrons flowing through the resistor. Common wattage sizes range from a quarter watt to 25 watts. Resistors are grouped in ohms and watt sizes. See figure 3-29. When purchasing a resistor, the desired resistance and wattage rating must be specified. For example, 1000 ohms and the watt size, 1/4, 1/2, or 2 watts, etc. In each watt size, the resistance value would be the same. Electrical power and wattage will be explained in detail in Chapter 4. See figure 3-30 to examine the construction of a molded composition resistor. Another type of small wattage fixed value resistor is the thin film resistor. The thin film resistor is similar to the molded composition resistor in appearance and function. However, the thin film resistor is made by depositing a resistance material on a glass or ceramic tube. A photographic process is used to deposit this thin film. Leads with caps are fitted over each end of the tube to make the body of the resistor. Thin film resistors are usually color-coded. The term film resistor is generally used to classify very compact resistors used in microelectronics or on very small-scale electronic circuit boards. Film resistors can also be referred to as surface-mounted resistors or SMRs. The demand for smaller and smaller electronic devices such as cell phones created the need for small discrete components such as resistors to be manufactured in a more compact method. Thick film and thin film are two general classifications based on how the film resistor is manufactured. Thin film deposits resistive material on an insulated substrate. The undesired portion is etched away, leaving the desired pattern of resistive material. See figure 3-31. Thick film deposits a special resistive paste directly on the insulated substrate by using a stencil or silk screen process. As a result, thick film is typically a thicker deposit of resistive material as compared to thin film. The advantage of thick film is the resistor can support higher currents and wattage than the thin film. The advantage of thin film is the smaller components requiring less heights can be made. The substrate is made from glass, ceramic, or silicon.
and it is used as an insulator base for the resistor. A layer of resistor material is deposited on the substrate in a zigzag pattern precisely engineered to produce the desired resistance value. The resistor materials are made from metals or carbon mixed in a precise proprietary formula. The result is a thin film, which is only a few micrometers thick, or thick film, which is 10 to 50 micrometers thick. A protective coating is used to cover the resistor material deposited on the substrate. The ends of the film resistor serve as the connection terminals and are made from metal such as nickel or silver, or they can be made from an alloy. Solder is used to mount and connect the film resistor to the circuit board. See figure 3-30. The process is very similar to the same process used to manufacture integrated circuits or ICs. The process is covered in more detail in Chapter 19. The number stenciled directly on the surface-mounted resistors indicates the resistance value. When a 3-digit number is used, the first 2 digits represent the first 2 digits of the resistance value, and the third digit represents the number of zeros to add to the first 2 digits. For example, the 202 in figure 3-32 represents the resistance value 2000 or 2K plus or minus 5% tolerance, meaning it's allowed to vary by 5%. When 4 digits are used, a tolerance of plus or minus 1% exists. For the 4-digit numbers, the same rule applies, that the last digit represents the number of zeros. For example, 5002 would represent 50,000 or 50k ohms, plus or minus 1% tolerance. For resistance values that require a decimal, a letter R is used to indicate the decimal point. For example, 7R would represent 7.5 ohms. Film technology is not restricted to single resistors, but may also be designed to produce resistor networks on a single chip. A resistor network consists of 2 or more independent resistors contained in one single surface-mounted package. For higher current uses, resistors are wire wound. A thin wire is wound on a ceramic core. The wire has a specific fixed value resistance. The entire component is insulated by a coat of vitreous or opaque enamel. These resistors are shown in figure 3-33. The wire-wound resistors are commonly manufactured in sizes from 5 to 200 watts. The wattage chosen depends on the heat dissipation required during operation. Metal oxide resistors are also used for high voltage and wattage requirements. Another type of wire-wound resistor is the adjustable resistor. Unlike the standard wire-wound resistor, the adjustable resistor is not entirely covered by enamel material. Instead, a portion, an adjustable sliding tab, is attached to move across the exposed surface. This allows the resistance value to be varied. The adjustable resistors may have 2 or more taps for providing various resistance values in the same circuit. An adjustable resistor and the symbol are shown in figure 3-34.
Potentiometer.
Most electronic equipment requires the use of variable resistance parts. A
Potentiometer
is a very common type of variable resistor found on electronic projects. The
potentiometer
has a rotary knob that varies the resistance value as it is turned. The variation in the resistance is provided by a contact that is attached to a ring of resistive material inside of the device. This device is similar to the wire-wound resistor. Many potentiometers are constructed with thin wire inside as the source of resistance. Various styles of potentiometers are illustrated in figure 3-35. Also shown is the potentiometer's schematic symbol. Thermistors. A special type of resistor is called a thermistor. In comparison to other types of resistors, a thermistor is unusual due to its ability to change resistance value rapidly as its temperature changes. It is commonly used to prevent high inrush currents in electrical circuits. An example of a thermistor can be seen in a blow dryer. A common blow dryer has heating elements composed of tungsten wire. Tungsten wire has a very low resistance value when cold and a high resistance value when red hot. The thermistor is placed in series with the heating element to prevent a high current value. When the dryer is first turned on, as the blow dryer heats up, the resistance value goes down. The result is a fairly consistent current value as the dryer heating element changes from low resistance cold to high resistance hot. Early blow dryer models caused a dimming or flickering of lights and other electronic equipment in the home because of inconsistent current draw. The thermistor eliminates this problem. Color code. Larger resistors are usually marked with their numerical resistance value printed directly on the side of the resistor. However, this type of labeling is not always practical, especially on small resistors. The resistor color code system
was developed for this purpose. The color code marking system has been adopted by the Electronics Industries Association, EIA, and the United States Armed Forces. This system of color coding is recognized throughout the world, referred to figure 3-36. Note how the color codes are printed or
banded
around the entire body of the resistor. This method of coding permits the value of the resistor to be read
regardless
of the mounting position. To see how to read the color-coded bands, refer to figure 3-37. Resistors commonly have 3 or 4, and sometimes 5 bands. Each band has a unique meaning. The first band represents the value of the first digit of the resistance value. The second band represents the second digit of the resistance value. The third band is called the multiplier. The multiplier gives the factor of
10
that the first 2 digits should be multiplied by. The fourth band represents the tolerance of the resistor. The resistor tolerance is a reflection of the position of the resistor's value. If a 20 ohm resistor has a 10% tolerance, the resistor's value can vary by plus or minus 2 ohms. In this case, the resistor can have a true resistance value of 18 to 22 ohms. A fifth band is sometimes used to indicate resistor reliability or expected failure rate. See figure 3-38. In the first sketch, the bar is red and the second bar is violet. Checking the color code chart shows the first
2 digits to be
2 and 7, or 27. This number is then multiplied by the third band. The band is brown, multiplied by 10. This indicates that the value 27 is multiplied by 10 for a final value
of
270 ohms. This is what the resistor value would be if the resistor was perfect. However, the fourth band is silver. This indicates that the resistor has a tolerance of 10%. In this example, the tolerance is a plus or minus 27 ohms. So 270 times 0.1 equals 27. Thus, the value of the resistor is sometimes between 243 ohms and 297 ohms. Work out the stated value, maximum value, and minimum value for the other two sketches in figure 3-34 on your own. For chapter 3 summary,
conductors
provide a low resistance path, while insulators provide a high resistance path. Factors that affect the resistance of a conductor are length, cross-sectional area, temperature, and type of material. A mil equals to 1/1000th of an inch. A circular mil equals the diameter expressed in mils squared, or d squared for a round conductor. Conductor insulation varies according to application. Switches are used to control the flow of electrons through a circuit. Switches are classified according to their actuator, internal electrical circuitry, poles and throws, ampacity, and voltage. Electric lamps may use filaments or ionized
gas
as a conductor.